Dear students, so in previous class we were discussing about the properties of supremum and infimum, and we say that infimum of A union B if is equals infimum of infimum A infimum B, supremum of A union B is supremum of supremum A supremum B, and so on. Now consider another one. Let A and B are any two non-empty subsets. A and B are any two non-empty subsets of R. Then, such that A less than B, A less than or equals B for all A fall in A and B fall in B. Then, supremum of A less than or equals infimum of B. This is an interesting research. If A and B are any two non-empty subsets of R, such that A less than or equals B for all A fall in A and B fall in B. Our requirement is then supremum of A less than or equals infimum of B. How to prove this one? The proof is, what is A and B? Come to the relation A less than or equals B for all A fall in A and B fall in B. That means this each element of B is an, what is B? B is an element of B. What is A? A is an element of it. Since A less than or equals B for all A fall in A and B fall in B, that means each element of B is an upper bound of this A. Sure. Since A less than or equals B, for all B fall in B and for all A fall in A, that means each element of B forms or be an upper bound of A. Each element of B is an upper bound of A means this supremum of A less than or equals B. Okay. For all B fall in B. Clear? Why? Since A less than or equals B, A is in A, B is in B. That is true for every A and B fall in A and B respectively. Therefore, every element of B, each and every element of B, be an upper bound of A. That means, so what about the supremum of A? Supremum of A less than or equals this B. Clear? So, that means supremum of A be a, supremum of A less than or equals B means, what is actually this supremum of A? Supremum of A be a lower bound of B. For all B fall in B, so by the definition of lower bounds, what is lower bounds? If S is a non-empty subset of R, then let any element W fall in R is said to be a lower bound of S if W less than or equals S for all S fall in S. This is the definition of lower bound. So according to that arguments, supremum of A less than or equals B for all B fall in B means this supremum of A is nothing but an element in R. So this supremum of A be a lower bound of B itself. Supremum of A be a lower bound of B means this supremum of A less than or equals infimum of B. Since supremum of A be a lower bound of B and that supremum of A less than or equals B, therefore supremum of A less than or equals the greatest lower bound of B means supremum of A less than or equals infimum B. Okay. So, now come to another research. Suppose S is a non-empty subset of R. Let S be a non-empty subset of R and which is bounded. Bounded means which is both bounded above and below. Then you can define S dash, where S dash equals, S dash is defined as S dash equals set of all minus X, set of all minus X, comma X of all in S. S is a non-empty subset of R and S is bounded means which is both bounded above and below, and define S dash equals set of all minus X for all X of all in S means the set of all negative elements negative of the elements which presents in S. That is called as S dash. Then we have supremum of S dash. Then, supremum S equals minus infimum S dash. S is a non-empty subset of R which is bounded, and S dash is defined as it is a set of all minus x for x of all in S minus x for x of all in S. Then supremum S equals minus infimum S dash. So this is an interesting result. How to prove this one? Here, given S is bounded. S is bounded. S is bounded means, so clearly it is bounded above. Since S is bounded above, it has a supremum. Okay, so let supremum of S equals some U. Let U equals supremum of S. Means U is an upper bound of S. U is an upper bound of S means x less than or equals U for all x of all in S. Clear? X less than or equals U means it is minus x greater than or equals minus U for all x of all in S. Clear? Minus x greater than or equals minus U for all x of all in S. So means minus x greater than or equals minus U means minus U less than or equals minus x for all x of all in S. Okay. Minus U less than or equals minus x, where U is a real number. Why? Because S is a subset of R. So there exists a real number which is less than or equal set of all minus x for all x of all in S. That means what is minus U? Minus U be a lower bound of S dash. Why? Because the elements in S dash is of the form minus x. So minus U be a lower bound of S dash. Clear? Lower bound for S dash. Again, let V be a lower bound for S dash. Let V be a lower bound for S dash. V be a lower bound for S dash means V less than or equals minus x for all x of all in S. Why? Because S dash is constructed as in this way. So V less than or equals minus x for all x of all in S. V less than or equals minus x means minus V greater than or equals x for all x of all in S. Okay, that means minus V greater than or equals x means x less than or equals minus V for all x of all in S. What is V? V be a real number. So there exists a real number minus V such that x less than or equals minus V for all x of all in S. So that means this minus V be an upper bound for S by the definition of upper bounds. Minus V be an upper bound for S dash. But what is U? U is the supremum of S. U is the least upper bound of S. Here minus V is an upper bound for S. That means this U less than or equals minus V. Why? Because U be the least upper bound for S. So U less than or equals minus V. U less than or equals minus V means this U less than or equals minus V. That means yes, this minus U greater than or equals minus U greater than or equals V. U less than or equals minus V means implies minus U greater than or equals V. That means V less than or equals minus U. V less than or equals minus U means V less than or equals minus U means what is this minus U? Minus U be the, so means minus U be the greatest lower bound for S dash. Okay, minus U be the greatest lower bound for S dash. That means minus U equals infimum of S dash. Minus U be the infimum of S dash means what is U? U is minus of infimum of S dash. What is U? U is supremum of S. That implies supremum of S equals minus infimum of S dash. Okay, this is what we recurse here. So if S is a non-empty subset and S dash is constructed in such a way that S dash equals set of all minus x for all x fall in S, then supremum of S equals minus infimum of S dash. Clear? So here supremum of S is U. That means x less than or equals U for all x fall in S by definition of upper bound. Means minus x greater than or equals minus U. That is minus U less than or equals minus x for all x fall in S. Then minus U be a lower bound for S dash. Why? Because there is the construction of S dash, which justifies the construction of S dash. So minus U be a lower bound for S dash. Let V be a lower bound for S dash. So V less by definition of lower bound, V less than or equals minus x for all x fall in S. Means minus V greater than or equals x for all x fall in S. That is x less than or equals minus V. That for all x fall in S, that means this minus V be an upper bound for S by the definition of upper bound. Since minus V be an upper bound, but U is the supremum of S, surely U less than or equals minus V. That means minus U greater than or equals V. That means V less than or equals minus U. So means minus U be a greatest lower bound for S dash by definition. That is minus U is the infimum of S dash. That is U is minus of infimum of S dash. What is U? That is supremum of S. The supremum of S is minus infimum of S dash. Clear? Agree? Now, the completeness property of form. The completeness property means if a set is bounded above for every non-empty set of real numbers, every non-empty set of real numbers which is bounded above has a supremum. Also, every non-empty set of real numbers which is bounded below has an infimum. Means if a set or subset of real numbers is bounded above, then it should have a supremum. If it is bounded below, then it must have an infimum. This property is called the completeness property of set of reals. Okay.